Welcome to the video lecture on logarithmic functions. Now remember that the exponential function is a one-to-one function, and therefore it has to have an inverse function. And that's what the logarithmic function is all about. So we're going to talk about how you find these logs and how you evaluate them. So let's start with a typical exponential function, which might have a formula that's of the form y equals a to the x. Now if we wanted to find out what its inverse function was, inverses swap x's and y's. So I could swap this y with an x, swap this x with a y, and then what we would want to do is try and solve this equation for y, which looks pretty impossible to do. How do you get that y down to the bottom level so that we can get y by itself? That's something that we don't know how to do. So what mathematicians have done is they've created a whole new function called the logarithmic function, which does exactly that. We're going to say that this exponent right up here, this y value, is by definition log base a of x. So here's what our definition for a log looks like. We say that y equals log base a of x if and only if, and that's what this double-sided arrow means, if and only if the base of the log raised to this power y would give you back x. So in other words, the log is what this exponent needs to be. So when you're finding a log, you're really finding out what the missing exponent should be. So we're going to practice this quite a bit. You need to be able to evaluate several logs by hand without using your calculator. And that's what all of these next examples are all about. So for example, let's figure out what log base 2 of 16 equals. And probably you're not too familiar with how logs work. So the best idea for simplifying these is to convert them into their exponential expression. So remember our definition up here? This would be the logarithmic expression, and this is its equivalent exponential expression. They mean exactly the same thing. Sometimes, though, it's easier for us to think in terms of exponentials than it is for us to think in terms of logs. So in a problem like this, what we're going to do is we're going to call this y, and we're going to try to rewrite this using exponential form. So the way you do that is you take the base of your log and you have to raise it to this missing exponent y that we're trying to find and figure out where that is going to equal this expression right here. And this is called the argument of the log. So this number 16 is the argument. So really, when it says what is log base 2 of 16, that's really the same question as saying 2 raised to what power is 16, because the log is the power. So 2 raised to what power is 16? Hopefully you can do that in your head. 2 raised to the 4th is 16. So the value of this log is 4. It just simplifies to a 4. Let's try another one. So if I want to know what log base 2 of 1/8 is, I'm going to call it y, and I'm going to rewrite this as an exponential expression instead of a log expression. So I'm going to take the base of my log, raise it to this unknown power, and call it 1/8. So you have to think about 2 raised to what power is going to turn it into a 1/8. And there's several ways to think about that, but hopefully you recognize that 8 is 2 cubed, but it's in the denominator. So how can we move that back up to the numerator? That's what negative exponents do. So 1 over 2 cubed is really the same as 2 to the negative 3. So the missing power that I need up here must be negative 3. Once I've made these two bases match, then I know what my power needs to be. So y needs to be negative 3. So think about that one more time. The negative is what's flipping you over, and the 3 is what's cubing the 2 to turn it into a 1/8. So that's why it works. Let's try another one. Log base 2 of 1. Let's call it y, and then we're going to change this to its exponential notation. So 2 raised to the y has to equal this argument 1. So 2 raised to what power turns it into a 1? There's only one number that does that, and that's the 0 exponent. So anything raised to the 0 turns it into a base of 1. Okay, let's try another one. So log base 4 of 8, if you want to figure out what that is, call it y and change it to an exponential form. So 4 raised to what power y turns it into an 8. Now on this one, this is a little trickier because 4 raised to some nice integer power does not turn into an 8. For example, 4 squared is 16, not an 8. That's already too big. So we know that we've got to think a little bit harder about this. And the trick to this one is to realize that both 4 and 8 are powers of 2. So we're going to try to rewrite both sides here using powers of 2 so we can try to get these base numbers to be the same. And if we can get the bases to match, then we know what the powers have to be. So we're going to change this 8 to a 2 cubed, and we're going to change this 4 to a 2 squared. But that 4 was being raised to the y power, so this is really a 2 squared raised to the y power. And power to a power, our laws of exponents say that you're supposed to multiply. So 2 times y would be 2y. So here's what our equation becomes. It's exactly the same as what we started with, but now it's in terms of base 2. Because the bases now match, the only way the bases can match is if the powers match as well. So that forces 2y to equal 3, and if I divide both sides by 2, that forces my power to be 3/2. So the value of this log has to be 3/2. 4 to the 3/2 power would give me back 8. Alright, let's try another one. Log base 2 of negative 1/2. Let's call this y and rewrite it. So 2 raised to what power makes it equal to negative 1/2. So think about that for a moment. 2 raised to what power makes it equal negative 1/2? Well, you might think that the answer is negative 1. You might say that y equals negative 1. And let's see why that might be a fairly good guess. Because 2 to the negative 1, what does a negative exponent do? It flips you over and turns you into 1 over 2. So the negative power would make us equal to this 1/2. However, it doesn't make that 1/2 negative. Is there any power that you can raise 2 to and get a negative answer back again? No, this is impossible. Whenever you take a base of 2 and you raise it to any power, no matter what number it is, that's going to stay positive. So this is impossible. So negative 1 is not our solution, and so we would just say that there is no solution. And what that means is that this is never going to be possible whenever this number in the argument right here is negative. It's impossible to take the log of any negative number because you can't take a base, raise it to a power, and ever get a negative answer back. So the log of a negative does not exist. Okay? Alright, let's try a couple of other ones that are equations here. So this is already written as a log equation. It's log base x of 25 equals to 2, and we're trying to figure out what x needs to be. So again, it's usually easiest to solve these by converting them into their exponential notation instead. And the way you do that is you take the base of your log, raise it to this power over here, and set that equal to the argument 25. So when does x squared equal to 25? Well, to solve that, normally we would take the square root of both sides, and we would get that plus or minus symbol, and we would get 5. However, if we allow the answer to be negative 5, then this base of this log would be negative. And we don't want that to happen. We never want to use negative bases. So we don't want negative bases for either exponentials or logs. So log base negative 5 of 25. That's not going to be allowed. So our only solution here then would just be the positive 5 case. And that should make sense why that works. Let's just double check our answer here for a moment. 5 squared does give me back this 25. So that's why it works. Okay, let's try one more example. Log base 5 of x equals to 4. So we're going to change this into our exponential notation. So the base 5 raised to the 4th power is supposed to equal this argument x. And that's really good because this is already solved for x. All we have to do is simplify what 5 to the 4th is, and that is 625. So we need 625 in for that argument. Okay, so the key to these, and you probably will be expected to evaluate logs like this on a test without a calculator. The key to these is setting that log expression equal to y, changing it into an exponential equation, and then solving that exponential equation. Sometimes you can just eyeball it and see what the solution is, but sometimes, like this one down here, you might have to do a little work to both sides before you can figure out what that power needs to be. Okay? The two logarithmic functions used most frequently are the common log function, which is log base 10, and we usually abbreviate that by just writing it as logx, so you don't even see that base 10 written in there. And if you look at a calculator, you'll see that most calculators have an log button. So that always implies base 10. The other common log that you will see is called the natural log function, and that's log base e. And again, mathematicians get a little bit lazy here. Instead of writing log base e every time, instead we write it as ln of x, and that stands for the natural logarithmic function. So if you look at your calculator, you'll see an ln button and you'll see an log button. Log is base 10, ln is base e. Okay, so those are going to be the only two log buttons that you have on your calculator with those specific two bases. So if you're trying to find the log of some other base, you're going to have to work around it somehow and convert it to either log base 10 or an ln. And we'll talk about how to do that in future lectures. So if we take a look at this next expression, it says write it in exponential form. So ln of the quantity x minus 1 is equal to 4. So the first thing you need to realize is that this ln implies log base e. And if you physically need to write it in there with that little base e to help remind you, do so. And if we're trying to write this in exponential form, that means we're trying to rewrite this as base e raised to the 4th power, and that's supposed to equal this argument, all this stuff in parentheses right here, so x minus 1. So that would be this log written in exponential form. Now if you wanted to take it one step further, you could actually finish solving this for x by just adding 1 to both sides. And so the solution to this logarithmic equation would just be e to the 4th plus 1. Okay? Let's go ahead and take a look at this example, and now we're going to go in reverse. So here's an exponential equation, and we want to write it in logarithmic form. Since the base of this exponential on the left-hand side is a base e, then that means we're going to want to use a log base e, and that is known as an ln. Okay, and if you need to write in that base e to reinforce that, please feel free to do so. So we need an ln. Now think about what needs to go here and what needs to go here. If this is going to be the correct logarithmic form, then e raised to this stuff over here needs to equal this argument right here. And what do we want e raised to? We want e raised to the x plus 1. So x plus 1 needs to go on this side, and that needs to equal 0.5. So 0.5 needs to be the argument. So just to kind of clean this up a little bit, this would look like ln of 0.5 equals x plus 1. So that's what this would be in logarithmic form. And again, if you wanted to take it one step further, you could go ahead and subtract 1 from both sides and write ln of 0.5 minus 1 equals to x, and finish solving for x. Okay, what we're going to talk about next here is how you can graph logarithmic functions. Now this information, these characteristics that we're going to talk about in just a moment, are the characteristics of the basic log function log base a of x. So this assumes that we don't have any transformations, no shifts, no flips, no stretches, compressions, anything like that. If you start doing those kinds of transformations, then some of this information may change. Now the first thing that we're going to notice is that the graph of log base a of x always contains the point 1, 0. And the reason for that is if we were to plug in 1 in for x, this would become log base a of 1. And we're saying that that has to equal 0. And the reason why is because a raised to the 0 would give you back 1. So that's why this is true. Likewise, if we plugged in a for this x, so that's what this point is referring to, what would this have to equal? It has to equal 1, because a raised to the first power would give me back a. So every log base a of x graph contains the point a, 1. And then finally, if I were to plug in 1 over a for this x, what am I going to get back? Well, I'm claiming that I get back -1, which is true because a raised to the -1 gives you back 1 over a. So both of these 2 points and this point will always be on your log base a of x graph. Now what do these graphs look like in terms of their shape? Well, if the base a is bigger than 1, then the graph is increasing. And it's going to look something like this. It's the reflection of the exponential growth graph over that line y equals x. So you have a graph that shoots down towards that y-axis and shoots up slowly towards the right. If you have a base that's between 0 and 1, which is also known as a fraction, then your graph is going to decrease, and this time it's going to start up high and come down low like this. Now if you'll notice, both of these two graphs have a vertical asymptote. Remember that exponential graphs have horizontal asymptotes, but since we're looking at the inverse now, the logarithm is the inverse, instead of horizontal, which would normally be y, now we're going to have x, which is vertical, for the asymptote. So remember, inverses swap, x's and y's. So if we used to have an asymptote on an exponential graph that was y equals a number, when we swap x's and y's, now that becomes x equals a number. So we're going to have vertical asymptotes on our log graphs. And as x approaches 0 from the right-hand side, on this graph here, the graph shoots down. That's what this statement here means. So as I approach 0 from the right, the graph shoots downwards. If the base is a fraction, then as I approach, oops, there's a typo here, as x approaches 0 from the right-hand side, then the graph should shoot up towards infinity. So this should say, as x goes to 0 from the right, this time our function will shoot up. And that's going to be this case right here when your base is a fraction. Now look at the domain and the range, and this is really important. If you look at these two graphs, notice that they are only having graphs for positive x values. I'm not seeing anything being graphed over here for these negative x values, regardless of which base I have. So the domain of every log function is 0 to infinity. Then if you look at the range, these graphs shoot all the way down and go all the way up. All the way down and all the way up. So the range is all real numbers. This is exactly the flip of what happens with an exponential function. In an exponential function, the domain is all reals and the range is all positives. For a log, the domain is all positives and the range is all reals. And that's because of that flipping or that swapping of x's and y's that happens with inverse functions. The function is 1 to 1. We can see that because it passes that horizontal line test, so it has to have an inverse function, namely the exponential. And all the previous transformations that we've talked about apply to log functions as well. Now we're going to talk a lot next about how to graph these, and this little table that I have right here is key. The best way to graph log functions by hand is to make a table of values using very specific x values. If you're trying to graph log base a, then your x values that you should use should be that same base a, 1 over that base a, and just 1. If you use these 3 inputs for your x, then you will end up with nice y's back again. And we'll see that in our next few examples. So let's take a look at this first graph, log base 4 of x plus 3. So the key to graphing these is to make a table of values. And my rule is log base 4 of x plus a 3. And the key to setting up this table correctly is the base of your log. This is a base 4. So automatically I'm going to want to use 4, that same base, 1 over 4, and 1. Those are going to be the 3 nice x values to use so that I get 3 nice y values back. So let's take a look at what we get back. We would plug in 4 for this x. So let's figure out what log base 4 of 4 is. And you may need to do a little bit of scratch work here for a moment. Think about log base 4 of 4. If you don't know what it is, think of this in terms of its exponential form. 4 raised to what gives you back 4? It has to be a 1. Okay, so this is going to go to 1. So we get 1 plus 3, which is going to give me back 4. Okay, let's try this again, but this time I'm going to plug in 1/4 for that argument. So doing a little scratch work again, we want to figure out what log base 4 of 1/4 is. So 4 raised to what turns it into a 1/4? What power flips 4 over and sticks it in the denominator? It has to be a negative. 4 raised to the negative 1 gives me 1/4 back. So this goes to negative 1. So we're going to get negative 1 plus 3, which is 2. And then finally, if I plug in 1 for that argument, then log base 4 of 1 would be 4 raised to what power turns it into a 1? Has to be a 0 exponent. 4 raised to the 0 gives you back a 1, so this goes to 0. So we're going to get 0 plus 3, which is just 3. So the 3 points that we're going to plot are 4, 4, 1/4, 2. So you have to estimate where 1/4 is on the x-axis and then go up 2 units. And then 1, 3. Now one thing we haven't talked about yet are the transformations that are going on here. So the only transformation that we see is a result of this plus 3 on the side. And it's off to the side. There's no parentheses here. It would be a very different kind of a shift if that 3 was in parentheses with that x. But since there's no parentheses, it's off to the side, which makes it a vertical shift. And because it's plus 3, this is going to shift our graph up 3 units. So that's the only transformation that we have. Now think about this. Let me go back to my graphs up here. If these are my typical log graphs, and this is the case we're looking at because a base of 4 is something bigger than 1, we want to see this graph shifted up 4 units. Now this graph has a vertical asymptote at x equals 0. Is that going to change if I shift my graph up 4 units? No. The only way this vertical asymptote will move is if I shift my graph left or right at all. So if there's only a vertical shift happening, then I'm still going to have a vertical asymptote at x equals 0. So draw in that little dashed vertical line that's not going to move. And this graph increases, but it shoots down towards that y-axis as I go closer to 0, and then slowly it rises up to the right. So there's a typical log graph right there. Slow rising to the right and shooting down towards that vertical asymptote on the left. Okay, let's try another one. So on this next example we have 2 ln of x minus 1. Let's do our transformations first this time. I see a 2 and I see a minus 1. What does the 2 do? Well, it's on the outside of your function. It's not timesing by the x, it's timesing by the entire function. So this is a vertical change. Because it's multiplication by 2, that's called a vertical stretch by a factor of 2. Okay? Same direction as you would expect because this is a vertical transformation. The minus 1 is off to the side. Again, there's no parentheses around it and the x. So it's off to the side of your function. That makes it a vertical shift, and in this case it's going to go down 1 unit. Now if you stretch your graph vertically, that does not shift your vertical asymptote at all. The only way you're going to shift your asymptote is if you shift the entire graph left or right, which this does not have any horizontal shifts. So I'm going to just go right ahead and write down my vertical asymptote at x equals 0 and put in those dashed lines so that I know not to cross that y-axis. Then to plot some points, I'm going to make my table of values, and what's key here is the base of our log. Okay, so since our base is e, since this is an ln, then the inputs that we want to use for x should be e, 1 over the base, and 1. So let's plug in e first. This is going to become 2 ln of e minus 1. And remember, ln is base e, so if you need to write in that base e, do so. And then I'm going to do a little scratch work on the side to figure out what this ln, which is a base e, of e turns out to equal. So e raised to what power is going to give me e back again? It's got to be a 1. So ln of e is just equal to 1. So this becomes 2 times 1, which is 2, minus 1, so the whole thing equals to 1. Now let's plug in 1 over e. So we're going to do 2 ln of 1 over e minus 1. And let's do our little scratch work. So what is ln of 1 over e equal to? I'm going to write in my little base of e. E raised to what power turns it into 1 over e? I need a negative. I need a negative 1 so that e to the negative 1 flips it over to a 1 over e. So all of this becomes a negative 1. So we get 2 times negative 1, which is negative 2, minus that 1 on the side gives me negative 3. And then finally, if I plug in 1, 2 ln of 1 minus 1, doing my scratch work, ln of 1, this is a base e, so e raised to what power turns it into a 1? Has to be 0. So ln of 1 goes to 0. And 2 times 0 stays 0. 0 minus 1 is negative 1. So the 3 points that I'm going to plot are e, comma 1. Now you have to remember e is approximately 2.7. So you want to be going over about 2.7 on your x-axis and then up 1 on your y. Then we want to plot 1 over e, and you want to remember that that's approximately 1 over 2.7 or 1 over 3. So 1 over e is about a third, so go over about a third on the x-axis, and then we're going to go down 3 on the y. And then finally we're going to plot 1 comma negative 1. So these are my 3 graphs. So the graph as a whole is going to look like these 3 points. They're wanting to rise up as I move to the right, so continue rising up. and they want to fall as I move to the left, but I don't want to cross over that y-axis. So you're going to skim the surface of that y-axis because you have that vertical asymptote. So there's our graph. Okay, let's try one more example. We have negative log of x minus 1. So what does this negative out front here do to my graph? When you have a negative out front of your function, not next to the x, but out front of your function, then that's a vertical type of reflection. So this is going to be a reflection that flips us upside down over that x-axis. Then we have this minus 1 on the inside, and this time we do have parentheses. So that minus 1 is next to that x, which makes this a horizontal shift, and it's going to go opposite of what we would expect. So a minus 1 means we're actually going to go right 1. Now think about that for a moment. As soon as you see that there's a horizontal shift, you have to think about how your vertical asymptote is going to move. Normally it would be right along that y-axis at x equals 0, but now we're shifting this entire graph to the right 1 unit. So the vertical asymptote is now going to get shifted right 1 as well, so it's going to be at x equals 1. So you can go ahead and draw in that dashed line through x equals 1. And that's the line that we don't want to cross. Now another thing that is made a little bit more difficult because of this shift right 1 is our inputs. Normally we would just make a table of values, and because this is log, remember this is called a common log, and if you see log, the implied base there is base 10. So normally we would use for our inputs 10, 1 over 10, and 1. But if you use those values, because of this shift, it's not going to give you nice y values back. What we're going to have to do is shift all of these to the right 1. So we're going to take those normal nice values and we're going to shift them right 1 and make them 1 bigger. And I'll show you why it works out nicely if you do this. So 10 shifted to the right 1 would become 11. 1/10 shifted right 1 becomes 1 and 1/10, and 1 shifted right 1 becomes 2. So we're actually going to use these 3 values for our nice x's and plug those in. So let's see what happens if we do. Let's plug in 11 for this x value. So using order of operations, do the subtraction first. 11 minus 1 becomes 10. And so when I go to do my subtract or my scratch work, I have log of 10, and remember common log means base 10. So 10 raised to what power gives you back 10? It has to be a 1. So log of 10 turns into a 1. But there's a minus in front of it. So this is going to become -1, a nice y value back again. And we wouldn't have gotten that nice cancellation if we hadn't used 11. If we had used 10, we would have gotten 10 minus 1, which is 9. And log base 10 of 9 does not simplify to a nice number. It's a decimal. So we have to use these shifted values to ensure that we get nice integers back. All right, let's try the next one. So let's plug in 1 and 1/10 for this x. So 1 and 1/10 minus 1 makes the 1's cancel, and it's going to leave us with just the 1/10. So when I go to do my scratch work, log base 10 of 1/10 is equal to what? 10 raised to what gives you 1/10? It has to be a -1 to flip the 10 over and turn it into a fraction. So log of 1/10 turns into a -1. But there was a negative already in front, so -1 becomes +1. Okay, finally, if we plug in 2 for our x, then 2 minus 1 is 1. So if I do log base 10 of 1, what is that equal to? Well, it has to be 0 because 10 to the 0 turns you into a 1. So this goes to 0, and -0 is still 0. So the 3 points that I want to plot are 11, -1. So that's a little bit off my graph, but it would be right about here. 1 1/10, which is just a little bit to the right of this asymptote, and then up 1, and then 2, 0. Now these aren't very many points, so if you needed to plot additional points, you certainly could. But what you want to notice is that these 3 points, they're sort of falling, they're decreasing. So you want to continue that pattern going to the right, and they're rising as I go to the left, and they want to skim that vertical asymptote. You do not want to cross that line x equals 1. Okay, let's try one more graph. We've got 2 log base 6 of x plus 1. So what does this 2 do on the outside? It's being multiplied, so it's going to be either a stretch or a compression, but because it's on the outside of my function and not right in front of my x, that's going to make it a vertical stretch, and it's a stretch because it's bigger than 1. So this is a vertical stretch by a factor of 2. Then we also have this plus 1 in parentheses next to that x, which makes it a horizontal shift. Because it's a plus 1, we're actually going to go left 1 unit. So as soon as I know that I've got a horizontal shift left or right, that means I'm going to be shifting my vertical asymptote as well. This line is going to move left or right with that shift. So if I'm going left 1, then my vertical asymptote moves left 1, and now it's going to be at x equals -1. So let's put in our dashed line. Okay, now that we have our asymptote placed, let's go ahead and get some points to plot. We're going to be using 2 log base 6 of x plus 1, and because this base is a 6, normally we would want to use 6, 1/6, and 1. But we have this shift left again. So whenever there's a horizontal shift, we need to apply that shift to our inputs as well. And we're going to need to shift all of these inputs to the left 1 unit. So what's 6 shifted left 1? It moves it down to 5. What's 1/6 shifted left 1? Well, it's 1/6 minus a 1, which makes it a -5/6. And what's 1 shifted left 1? That moves it to 0. So those are going to be the new inputs that we want to use to ensure that we get nice y values back. So let's plug in. We get 2 log base 6 of 5 plus 1. When I add there, 5 plus 1 is 6, and by now hopefully we can figure this out in our head. 6 raised to what power would give me back a 6? 1. So this log base 6 of 6 is just a 1. And you'll start to see that as a property here. Anytime the base down here matches this argument, they're going to cancel each other out, giving you just a 1. So we get 2 times 1 is 2. Now let's plug in -5/6. So we get 2 log base 6 of -5/6 plus 1. Well, 1 minus a 5/6 is 1/6. So if this is base 6, 6 raised to what power turns it into a 1/6? That's got to be that negative exponent. So -1. And we get 2 times -1 is -2. And finally, if I plug in 0, 0 plus 1 stays 1. So we get log base 6 of 1. So 6 raised to what power turns it into a 1? It's got to be a power of 0. And 2 times 0 stays 0. So here's our points that we're going to plot. 5, 2. -5/6, -2. So just a little bit to the right of that asymptote, and then down 2, and then 0, 0. These points right here at 2 and -2 are stretched up a little higher than they normally would be because we were multiplying by 2 on the outside. So there's that vertical stretch in action. Then if you look at these 3 points, they're slowly arcing to the right, and they're slowly falling towards that asymptote as you go down. Okay, let's take a look at this next example. List the transformations and find the vertical asymptote for ln of 2 minus 3x. So if we want to find the transformations correctly, what you gotta notice right off the bat is this has a coefficient in front of that x. So that coefficient has to be factored out correctly before you start figuring out what your transformations are. If you need to, switch the order around to put the x term first. So this would be a -3x plus a 2. And what I'm going to do is factor out that -3 from the parentheses. I would be left with an x. I need a minus times a minus to give me this plus 2. And 3 times what gives you back a 2? It's got to be a 2/3. That way the 3's will cancel, leaving me with just a 2. So this function is really the ln of -3 parentheses x minus 2/3. So what are the different transformations that are going on here? Well, we have this negative inside next to that x. So that makes it a horizontal reflection, which makes it a reflection over the y-axis. We also have this 3 next to that x. It's being multiplied, so that's going to make it either a stretch or a compression. But because it's multiplied by the x, that makes it a horizontal change, and horizontal ones go in the opposite of what you would expect. So instead of multiplying by 3, which would normally we would think of as a stretch, this is actually going to be a compression by a factor of a 1/3. And then finally over here on the right, again next to that x, so it's in the horizontal direction, we are going to have a horizontal shift. It's a minus, so we're actually going to go right 2/3. So those are my 3 different transformations, and because we're going right 2/3, that would shift the entire graph to the right 2/3, including that asymptote. So that changes our vertical asymptote, and instead of being at x equals 0, it's going to move it 2/3 to the right, so our vertical asymptote would be x equals 2/3. So here's our 3 transformations, and here's our vertical asymptote. Okay, the next example. Find the domain of the function ln of x squared minus 3x. Now remember, for ln graphs or any kind of log graph, if the base is bigger than 1, you have an ln graph that increases. So this is if the base is bigger than 1. If the base is a fraction, you have a graph that decreases. Those are your 2 common shapes for a log graph. What's common about both of them is that they only have graphs for positive x values, and that's because the domain of a log graph is normally just 0 to infinity. What that means is this argument, this stuff right here, has to be a positive value, because those are the only x's that we're allowed to plot ln's of. So we have to make sure that in order for this ln to exist, this stuff right here must be something positive. So this quantity, x squared minus 3x, must be greater than 0. It can't even equal 0, because at 0 itself is where we had that asymptote, which was undefined. And it's never negative because we don't have any part of our graph over here. So your argument always has to be something strictly greater than 0. So when does that happen? When does x squared minus 3x lie greater than 0? Well, there's several ways to figure that out, but one fairly easy way to do it is to think about the graph of x squared minus 3x. If you call it y equals x squared minus 3x, that's a parabola because of the x squared, And it's pretty easy to factor because I can just pull out an x, which means that it has x-intercepts at 0 for this x factor and at 3 for this factor right here. All I'm going to try to do here is make a really rough sketch. I know that this parabola is hitting the x-axis at 0 and at 3. I'm not going to waste my time and try to find a vertex. All I care about is whether or not this parabola should point up or point down. Because it's a positive x squared, this has to be a parabola that points up. And I don't really care how low it goes, I just need to know its general shape. Now once I know its graph, what we're trying to find on that graph is where on that graph does it lie above 0. Well, here's 0. Where does the graph lie above it? For all of these points and all of these points, which correspond to all of these x's and all of these x's. These x's would be minus infinity up to 0, and these x's would be from 3 to infinity. Notice that I'm using parentheses around those endpoints because we want this strictly greater than 0. We don't want it to actually equal 0. So I need for my domain both of these sets. So here is the domain. These are the values of x that are going to make this quantity be something positive, which I can then take the ln of and have that exist. So the domain is minus infinity to 0, union 3 to infinity. Okay, in our last little comment down here, just a review of some of the properties that we talked about today. This first one, we can generalize and say that the log of 1 is always 0, no matter what the base happens to be. And the reason for that is because a raised to the 0 will always equal to 1. Similarly, a raised to what will always give you back a? 1. So that means log base a of a is always 1. And one way that I remember this is it's kind of like a cancellation property. As long as the base of your log matches your argument, as long as these two things match, then it'll cancel to a 1. So similarly, if these two match, they're going to cancel out, but I'll just have this x left over. And you can see why that would be true, because a raised to the x would give you a to the x back again. And then this one is the same idea but in reverse. So instead of taking the log of an exponential and having that log and exponential cancel out, here we're taking an exponential of a log. So as long as these two numbers, the base of the exponential and the base of the log, match, then the log and the exponential will undo each other, cancel each other out, and you'll just get x back again. So those are just a couple of special cancellation properties of the logarithmic function, and you might want to have those memorized. All right, good job. We're all done with our lecture on logarithmic functions. Good luck.